let's look one more example. So in this example, it looks, oops, you can't see it. It looks even more innocent than the last one. It's the fourth derivative plus the unknown function equals 0. Just solve it, find the general solution. But we'll see, this gets us into some tricky, complex number stuff that we have to remember how to do, or maybe learn how to do for the first time for some of you. Okay. So if you write down the characteristic equation for this would be lambda to the fourth plus 1 equals 0. So that says lambda to the fourth is minus 1. So that's an eigenvalue of multiplicity 4 is the, you have the, basically, you have to find 4, well, I said that, scratch what I just said. This says lambda to the fourth is minus 1. In other words, we have to find 4 roots of minus 1. Now, if you only work with real numbers, you can't do that at all because you can't find the square root of a negative number. So you need 4 roots of minus 1. But in complex numbers, you can do that. So let's remember a little bit of the stuff we learned about complex numbers before. Every complex number can be written in the form a plus b times I, right? And let's call that z. And it can also be written as the absolute value of z times e to the I theta. This is called a polar decomposition. Every complex number has a polar decomposition. Okay, remember what e to the I theta was? It was cosine theta plus I sine theta. So it's convenient to remember the polar decomposition this way, although sometimes we're going to work with things this way because we know we're more familiar with sine and cosine. And the z, when z is a plus bi, the absolute value of z, or they call it the commonly used term for in complex theory, is modulus. The modulus is a squared plus b squared. Okay, so that's these two coefficients squared. Okay. So in order to find roots of minus 1, I want to think of minus 1 in its polar decomposition form. Okay, so I have to think of it as a plus bi, where a is minus 1 and b is 0. Because when you look at minus 1, you see the real number and there's nothing times I. Okay. So the modulus, or the absolute value of minus 1, is plus 1. We didn't really need this theory to tell us that. We knew that. Okay. And so minus 1 can be written as the absolute value of minus 1. I'm using the polar decomposition here, times e to the I theta. And we got to think about that for a minute. This one is 1. So let me see. So this is equal to e to the I theta, which is cosine theta plus I sine theta. So you need to know your trig well enough to be able to answer which value of theta gives you minus 1 when you write it this way. Well, you want the sign of that to be 0 because you need the complex term to go away. And you want the cosine of whatever theta you're going to use to be minus 1. The cosine is minus 1 at pi. So this works when theta equals pi. Okay, so you can write, because of that. Okay, so we can write minus 1 in a fancy way as cosine theta plus cosine pi plus I sine pi. Okay. Now you may be thinking, why in the world do you want to write a number as nice as minus 1 as cosine pi plus I sine pi? But hang on, you'll see we have to find the 4th roots of this. So the trick comes when you realize that cosine and sine are 2 pi periodic. So if I add any multiple of 2 pi in its argument, it's the cosine of that number stays the same and the sine of that number stays the same. In other words, the cosine of pi plus 2k pi is the same as the cosine of pi. And the sine of pi plus 2k pi is the same as the sine of pi because sine is 2 pi periodic and so is cosine. And we want even multiples. I don't know if you can read this very well. This is a 2k. This is 2k pi. Okay. So you want even multiples to make sure it's 2 pi periodic. So you want to put the 2 in there to make sure it's even. All right, so that now it's convenient. Sometimes it's better to write it in the cosine form, sometimes in the exponential form. Now we want to actually start finding the roots. Now you have to go back to the exponential form. So cosine this guy plus I sine the same guy is e to the I, that guy. Okay. All right. So now we want to solve lambda to the fourth is -1. Lambda to the fourth is -1. And we wrote -1 this way. So now take the 1/4 power over on the left and over on the right. So when you take the 1/4 power, that is, you're finding fourth roots of -1, you have to take the 1/4 power of that exponential. But when you have, you're taking the power of something that has an exponent like that, you multiply the exponents. So this becomes e to the I, now I'll start multiplying through, pi over 4 plus k pi over 2. Oops, let me get that up high enough. So I just multiplied the 1/4 times what was inside. Okay. And now I go back to my sines and cosines. So that's cosine pi over 4 plus k pi over 2 plus I sine that same thing. Okay. Right. Now, how do we actually start finding the roots? That last little expression there for you. Try to get everything there. Okay. So you need 4 roots. You get the first root by taking k equals 0 in this formula. Okay, so when I take k equals 0, I get lambda is cosine pi over 4, because k is 0, plus I sine pi over 4. Okay, and now what's the cosine of pi over 4? 1 over the square root of 2. And what is the sine of pi over 4? 1 over the square root of 2. Okay, so I can write it this way if you like, or you can leave it like that. Either way, whatever makes you happy. Okay. To get the second root, we take k equals 1 in this formula. Okay, now when k equals 1, you get cosine of pi over 4 plus pi over 2, and sine of pi over 4 plus pi over 2. Okay, so now when you add those together, that gives you sine and cosine of 3 pi over 4 in this combination. What's the cosine of 3 pi over 4? Well, that's the 45-degree angle in the second quadrant. So cosine's negative, but sine is positive, and 45-degree angles are always plus or minus 1 over the square root of 2. So the cosine is negative, 1 over the square root of 2, and the sine at 3 pi over 4 is positive. So you can leave it like this, you can write it like this, whatever makes you happy. Okay. Now I think I'm going to need to do this. Now we need the third root. So we got the first root by k equals 0, second root by k equals 1, the third root by k equals 2. You play the same game, you plug in k equals 2, write down what you get. You will do fine with these problems if you learn the process and you write things down a lot. I saw a lot of people lose a lot of points because they were trying to skip steps or not write equal signs and they got lost in their own calculations. Don't be that person. Write your steps down. It doesn't take that much longer and it lets you get the answer right. So now I'm doing with k equals 2. So I'll write this down when k equals 2. And what is pi over 4 plus pi? That's 5 pi over 4. So write that down. And now start to think, what's the cosine and sine at 5 pi over 4? That's a 45-degree angle in the third quadrant. In the third quadrant, sine and cosine are both negative. So this is minus 1 over the square root of 2 plus I times the sign there is minus 1 over the square root of 2. Okay. And then finally, to get the fourth root, you take k equals 3, play the same game. K equals 3 gives you pi over 4 plus 3 pi over 2. So that turns out to be, you need the sine and the cosine at 7 pi over 4. That's 45-degree angle in the fourth quadrant. So their cosine is positive and sine is negative. Okay, so now we have our 4 roots. And now let's look at these roots all together and see how they fit together. If I can get it on one screen. Okay. Okay, there we go, a bit. Yes. Almost. There. Okay, so notice that the first root, 1 over the square root of 2 plus I times 1 over the square root of 2 is the complex conjugate. This root and this root are complex conjugates of each other. There. Okay. So the first and the fourth occurred in a complex conjugate pair. So you think of that as 1 over the square root of 2 plus or minus 1 over the square root of 2 times I. Okay. So what kind of solutions did you get when you had a term like that in the second order equations? What you got was e to the 1 over square root of 2, because that's the real part. And then you would get the sine and the cosine with the 1 over the square root of 2 in it. You need to get both of them because of the complex conjugate pair. So here's one set of solutions of the sorry, it's not showing. Point to something you can't see. You get an e to the real part. Remember, this is, you have a complex, the roots look at 1 over the square root of 2 plus or minus 1 over the square root of 2i. That's the pair of roots we're thinking of right now. So this is the alpha and there's the beta. And so you would get a solution that looks like this, with this exponential out in front and the sine and the cosine at 1 over the square root of 2. Okay, so this is one pair, that's 2 linearly independent solutions to that fourth order equation. But you need 4, it's a fourth order equation. So now look at, I don't know, I need to use another sign, plus sign, this one and this one. Okay, those 2 roots are complex conjugate pairs of each other. They are the form minus 1 over the square root of 2 plus or minus 1 over the square root of 2 times I. So now here alpha is minus 1 over the square root of 2 and beta is the same as it was before. What kind of solutions did you get for a second order equation when you had that? You would get an exponential with a e to the minus t over square root of 2. And then because of this guy, you would get a sine and a cosine with a 1 over the square root of 2 times t. So there's 2 more linearly independent solutions. So now your general solution is a linear combination of those 4 solutions. Okay, so that's kind of a lot to absorb because you have all this business of finding the roots of a complex number, finding the powers of a complex number, which takes a little while to get used to. And you're going to have to do several problems like that to get used to it. Okay, so I think that's enough. That's the first section and the second section. That was all done in that previous lecture. We're going to stop here. And on Wednesday, I'll upload another section 4.3, and I'll adjust the homework deadlines a little bit for all of this. Okay, so sorry about the confusion. It's really one lecture mostly, but they are they're going to have to be broken up into sort of 40-minute sections. So we'll do 2 40-minute uploads instead of one 85-minute. One might be 45 or something like that. Okay. And then next Monday, we will have an online session. I'll set up a meeting for questions on homework problems. Okay. Have a good week, a good couple of days, and I'll see you again on Wednesday. Okay. Bye.